I don't want you to think relativity is some mysterious, untouchable thing. It's actually quite simple if you think about it correctly. And the reason I want to talk about it is because it shows you why something that seems like it should be possible, going to another star, is actually fundamentally blocked by the laws of physics. It's a beautiful example of how nature puts limits on us. So let me start with something simple. What is speed? Well, speed is how fast something is moving. You go 60 miles per hour, that's your speed. Now, here's where it gets interesting. When I talk about speed, I'm always talking about speed relative to something else. The Earth is moving, the Sun is moving, the galaxy is moving. So really, there's no such thing as absolute speed. Speed is always relative. Now, Einstein said something remarkable. He said, and I want you to really think about this, the speed of light is the same for everybody. Not approximately the same, exactly the same. 300,000 kilometers per second. It doesn't matter if you're sitting still or if you're moving very fast. The speed of light is always the same. This seems crazy at first. If a train is moving at 60 miles per hour and a ball is thrown forward at 30 miles per hour, then relative to the ground, the ball is moving at 90 miles per hour, right? Okay, so you'd think if a spaceship is moving at half the speed of light and shoots a beam of light forward, the light would be moving at 1.5 times the speed of light. But it's not. It's still just the speed of light. This is not intuitive. Your everyday experience doesn't prepare you for this. But it's true. And because this is true, that the speed of light is constant for everybody, time and space have to behave in very peculiar ways. Here's what happens. Imagine you're watching a spaceship zoom past you. Let's say it's going very, very fast, really close to the speed of light. Something strange happens. From your perspective, time on that spaceship appears to run slower. Much slower. This is called time dilation. Now here's the beautiful part about this. It's not just that the clock looks broken or something. The time really does run slower. If I put a person on that spaceship and that person has a heart, that heart really does beat slower, from my perspective watching from the ground. And what's truly remarkable is that to the person on the spaceship, everything seems normal. Their heart beats at a normal rate. Their clock ticks at a normal rate. But to me, everything looks slowed down. The way the universe makes this work is through a mathematical relationship. If something is moving at a velocity v and the speed of light is c, then the time on that moving object runs slower by a factor of 1 over the square root of 1 minus v squared over c squared. I know that sounds complicated, but let me show you what it means in practice. Let's say you're going at 90% the speed of light. What does the time dilation factor become? Well, v squared is 0.9 squared, which is 0.81, and c squared is just 1. So v squared over c squared is 0.81. 1 minus, that is 0.19. The square root of that is about 0.44. So 1 divided by that is about 2.3. This means time on your spaceship runs about 2.3 times slower than on Earth. So for every year that passes on your spaceship, more than 2 years pass on Earth. Now let's crank it up. What if you're going at 99% the speed of light? Then v squared over c squared is 0.98. 1 minus, that is 0.02. The square root is about 0.14. 1 divided by that is about 7. So time runs 7 times slower on your spaceship. For every year you age, 7 years pass on Earth. 99.9% the speed of light. Now we're getting into really crazy numbers. The time dilation factor becomes over 70. For every year of your time, 70 years pass on Earth. Now, you might be thinking, okay, that's interesting, but so what? Well, here's the so what. Think about what you need to do to get a spaceship to move this fast. You need energy, a lot of energy. Let me give you a concrete example. Let's say we want to send a spaceship to Proxima Centauri. It's the closest star to us, about 4 light years away. That means if you're traveling at the speed of light, which you can't do, but let's pretend, it would take 4 years to get there. Now, suppose we want to make this trip in just 5 years as measured by the astronauts on the spaceship. We want them to experience only 5 years, even though they're going 4 light years. That means we need to choose a speed such that the time dilation factor is high enough that 5 years of spaceship time corresponds to about 4.5 years of Earth time, roughly. If you do the calculation, you find you need to go at about 99% the speed of light, maybe higher. You're right up against that cosmic speed limit. Now here's the problem. Let's think about a spaceship about the size of a 747 aircraft. Pretty reasonable for an interstellar mission, right? You need room for people, supplies, fuel, equipment. A 747 weighs about 400,000 kilograms. To accelerate this spaceship to 99% the speed of light requires energy. And not just a lot of energy. I mean a truly incomprehensible amount of energy. When you calculate it using Einstein's formulas, the energy needed is something like 70 quadrillion kilowatt hours. Now what does that number mean? Well, the entire United States, all the electricity, all the gasoline burned, all the natural gas used, all the energy consumed in any form for an entire year in the year 2022. That's about 15 trillion kilowatt hours. To get to Proxima Centauri in 5 years with a 747-sized spaceship going at 99% light speed would require about 4,800 times the total energy consumption of the United States for a whole year. Let me say that again so you really hear it. One mission, one spaceship, for 1,800 years worth of all energy that the United States uses. And that's just to get up to speed. That's not including slowing down when you get there. That's not including any energy to keep you alive or run anything on the ship. That's just acceleration. Now, you might think, well, okay, we can make the spaceship smaller. Sure, let's say instead of a 747, we send something the size of a motorhome. It weighs about 4,500 kilograms. That's much smaller. So the energy required should be much less, right? Wrong. It's still enormous. Because the relationship between kinetic energy and velocity is exponential when you're approaching the speed of light. Making the ship 1,000 times lighter doesn't make the energy requirement 1,000 times smaller. It's still utterly impractical. You still need energy that no human civilization is realistically going to harness in any foreseeable future. And here's the other thing that nobody talks about much. There's the energy problem. But there's also another problem that gets worse as you go faster. When you go really fast through space, you're moving through a lot of stuff. There's cosmic dust. There are particles. Even if space seems empty, it's not really empty. There's the cosmic microwave background radiation, particles of light left over from the Big Bang. At 99% the speed of light, these particles that seem harmless when you're moving slowly become like high-energy cosmic rays hitting your spaceship. They hit with tremendous force. They would damage the ship. They would damage the shielding. It would take more energy just to protect yourself. So you see, the faster you go, the more problems you create. You need more energy to accelerate. You need more protection from radiation. You need stronger shields. All of that adds weight. And weight requires more energy to accelerate. It's a vicious cycle. Now, let me tell you about another problem that relativity creates. It's called the relativity of simultaneity. This is really interesting if you think about it. Here's the idea. Let me paint a picture for you. Imagine I'm standing on Earth and you're on a spaceship moving very fast. I measure two events happening at different locations and I say, these two events happened at the same time. You might disagree with me. You might say, no, one happened before the other. And you're right. And I'm right. We're both measuring the same events. But because of how relativity works, the order in which events happen depends on who's observing. This actually becomes important for interstellar travel, because if you're moving fast enough, causality can get weird. Not backwards, but weird in a way that suggests the universe really doesn't like it when you move too fast. Things would have to happen in strange sequences. Now, here's something I find absolutely beautiful about all this. It's not that these are arbitrary rules that God decided to impose. There's a reason for all of this, and it comes from one simple fact. The speed of light is constant. Think about what that means. If the speed of light is truly constant for everyone everywhere, then as you move faster, time has to slow down. That's not an arbitrary rule. That's a consequence of that one fact. It's like how if you decide that parallel lines never meet, then certain geometric theorems must follow. You can't escape them. And as you approach the speed of light, time doesn't just slow down a little bit. It slows down more and more. The closer you get, the slower time runs. And at the speed of light, actually reaching it, time would stop completely. It just stops. So what does this mean? Well, it means something very simple. Nothing with mass can reach the speed of light. I'm going to say that again because it's important. Nothing with mass can reach the speed of light, because to do so would require infinite energy. The energy requirement just keeps growing and growing as you go faster. Now, a long time ago, people thought of things differently. They thought you could go as fast as you want if you had enough fuel. But no, there's a cosmic speed limit. And it's not because we haven't invented good enough rockets. It's because the universe itself is built this way. Photons, particles of light, they have no mass. That's why they can move at the speed of light. In fact, they have to move at the speed of light. But anything with mass, anything with inertia, anything that takes energy to accelerate cannot reach that speed. So let me go back to our interstellar problem. You want to go to the stars. You think maybe in a few hundred years or 1,000 years, humanity will be much more advanced and we'll find a way. But here's the thing. We can't build our way out of this problem. This isn't about technology that we haven't invented yet. This is about the fundamental structure of reality. It's like asking, can we build a machine that goes back in time? There's no machine that can do that. Some physicists think time travel backwards might be possible in principle, but it would require exotic matter and strange solutions to Einstein's equations. But certainly a regular machine can't do it. In the same way, a regular spaceship can't exceed the speed of light. Now, there are science fiction ideas. People write about warp drives. A warp drive would somehow contract space in front of the ship and expand it behind the ship. So you're not technically moving faster than light through space, but you're still crossing distances faster than light travel would allow. But here's the problem with warp drives. They require something called negative energy or exotic matter. We've never found negative energy. We don't know if it exists. And the amounts required would be enormous. You'd need more exotic matter than exists in the observable universe to create one warp drive. So okay, interstellar travel seems impossible. But wait, let me tell you about something interesting. There's a loophole, and that loophole is time dilation again. Imagine you don't actually care about getting somewhere in a short time on Earth. You only care about getting somewhere in a short time for the people on the spaceship. This is actually possible. If you can get to, say, 89% the speed of light, the time dilation factor is about 2.3. That means for every year of spaceship time, 2.3 years pass on Earth. Now imagine you're going to Proxima Centauri for light years away. At 89% light speed, the trip takes about 4.5 years of Earth time. But on the spaceship, it only takes about 2 years. 2 years. The astronauts barely age. They leave Earth. They travel for 2 years of their time, and they arrive at Proxima Centauri. The problem is still the energy, of course. You still need enormous amounts of energy to accelerate to that speed. But at least, from the astronaut's perspective, the trip is quick. Imagine going even faster. Suppose you got to 99.9% the speed of light. The time dilation factor would be more than 70. The trip to Proxima Centauri would still take 4 light years of Earth time, so about 4 years. But for the astronauts, only about a month would pass. A month. They could travel to Proxima Centauri in a month of their time. This is actually kind of wonderful, isn't it? It solves part of the problem of the astronaut's lifespan. They don't age much during the trip, but it doesn't solve the energy problem, and it doesn't solve the radiation problem, and it makes a new problem worse. You see, if you're traveling at 99.9% the speed of light, space becomes very dense in front of you. The cosmic microwave background radiation particles, the cosmic dust, all of it gets compressed due to the relativity effect called Lorentz contraction. From your perspective, moving very fast, the universe in front of you looks compressed. The radiation is more intense. The dust particles hit you with even more force. You'd need incredibly strong shielding. That adds weight, and it would generate tremendous heat. You'd need to radiate away that heat somehow. It's an engineering problem that seems to compound all the others. And there's something else. As you get closer and closer to the speed of light, the amount of energy you need to accelerate further becomes enormous. Getting from 99% to 99.1% light speed requires vastly more energy than getting from 0 to 10% light speed. So basically, the universe is built in this beautiful system of constraints that says, you know what? Interstellar travel is really hard, nearly impossible. It's not impossible in principle. Einstein's equations don't forbid it, but it requires resources that are unrealistic. It requires energies that are enormous. It requires technologies that we can barely imagine. It requires accelerations that might be dangerous. And it requires shielding against radiation that we don't have. Now, you might ask, well, maybe there's another way. Maybe there's something else we don't know about. And sure, maybe. Science is always open to new discoveries. But it would have to be something fundamentally different from what we know. It would have to violate the principles we've tested thousands of times and found to be true. Some people talk about wormholes, which are theoretical tunnels through space-time. But to create a wormhole, you'd need to control gravity itself, which we can't do. You'd need materials we've never found. And Einstein's own equations suggest you'd need more mass energy than the observable universe contains. Some people talk about suspended animation. You put the astronauts to sleep, and they sleep for the whole journey. It doesn't require as much energy if you're going slower. But you still have radiation damage to worry about. And you still have the problem that it takes decades or centuries of Earth time for the journey. Some people talk about generation ships. You launch a spaceship with people, and they die, and their grandchildren die, and their great-grandchildren finally arrive at the destination. It's possible in principle, but it's a very different kind of space travel. It's not exploration, it's colonization. But here's what I find fascinating about all this. The more we learn about the universe, the more we learn about the laws of physics, the more we discover that there are these hard limits. And these hard limits aren't bugs. They're features. They're part of how reality works. Special relativity tells us something deep. It tells us that space and time are not separate things. They're woven together. And because of that deep connection, there are limits on how fast you can move through space. And thinking about this more broadly, it makes you appreciate Earth in a way. We're not going to casually visit other star systems. We're not going to have regular trade routes to Proxima Centauri. We're not going to have colonies scattered throughout the galaxy, at least not in any normal way. That doesn't mean we're stuck here forever. Maybe someday, if humanity survives and gets smarter and builds incredible technology, maybe we'll find a way. Maybe there's something in the nature of reality that we don't understand, yet that would allow it. But it won't be easy. It won't be casual. It will be one of the greatest achievements imaginable if it ever happens. And maybe that's okay. Maybe the fact that the stars are hard to reach is one of the things that makes them worth reaching. It's one of the things that makes them special. So that's the thing about special relativity and interstellar travel. It's this beautiful, frustrating lesson from nature. The universe is telling us, you can move around in space, but not infinitely fast. And the closer you get to the speed limit, the more you pay, the more energy you need, the more your time slows down, the more hostile the universe becomes. It's a speed limit, not a law that a cop could enforce, but a law written into the very fabric of existence. And I find that remarkable.